Dear students, welcome to Digital System Design using Verilog class. So in today's class we will be seeing into some more different types of memories like ROM. In the previous class we have discussed about RAM, random access memory. So today we will be going through ROM. This is another type of memory. Unlike RAM, here it is not possible for us to write our data into the memory. That's why this is called as read-only memory. We can only read the contents of the memory. That's why these type of memories are suitable for keeping the CPU programs. Right? So there are different types of ROMs available: masked ROM, programmable ROM, and erasable ROMs. Okay, masked ROMs are data is manufactured into the ROM. Okay, programmable ROM is we can program and we can write the data into this ROM. That is why it is called programmable ROM. Erasable ROM is we can write the data into the ROM and we can be able to delete the contents of the ROM through UV, that is ultraviolet rays will be made to fall on the memory to eliminate or erase the contents of the memory ROM. So electrically erasable, by passing the electrical signals it is possible for us to remove the contents of the memory. And also there is another type of RAM which is called as flash RAM. So coming to this combinational ROM, so in this we will be mapping the address input to the data output. So address input gets mapped onto the data output. So that's why this is called as combination of address to the data output. Okay, so one best example is 7-segment decoder. Okay, have a look at this. Address is A0 to A3, 4-bit address. A4 is used for blank. Okay, so 4-bit BCD data is taken as an input. For example, address 0 is getting mapped onto the content. Content is this 0 followed by 6 ones, right? So when the address is 1, this is going to be the data. When the address is 2, this is going to be the data. That means whatever the display we need to get on the 7-segment and which are all the segments that we need to make high, those bits will be enabled. Okay, when address is 3, this is going to be the output. So that's how we will be mapping the address to the data, right? So if you have a look at this Verilog program for random access memory, by taking 7-segment decoder as an example, module, a name has been given 7-segment decoder. We have defined the output which is called as SEG segment, which is a 7-bit variable. Seg is 7, so 7 down to 1 is totally 7 bits. So BCD is 4-bit input, 3 down to 0 is 4-bit, blank is 1-bit input. Okay, now we are starting a behavioral way of programming where it starts with always block. Always is a procedural block. Always at asterisk says bring all the inputs into the sensitivity list. That means when any of our input changes, it should affect the programming corresponding output. So case blank comma BCD, take these two variables into the case statement, and as you can see here, 5-tick binary 0000 means this is a blank data and this is going to be the BCD code. If this is a case, that means if the address is 0, then this should be the output. Segment is equal to this. From the previous slide we have understood that if this is the address, okay, if this is the address, then this is a content. Likewise, we are writing that in the case statement. So second case is if this is the address, then data is this. Segment is assigned with 7-tick binary 00001110, that is 7-segment value for displaying 1. Next case, if this is an input, segment is assigned with these values, which is nothing but the value to display a numerical value 2 on a 7-segment display. Likewise, this many cases have been written over there. When none of the cases have been encountered, by default segment is made equal to blank. Okay, So this is one of the scenario when none of the cases match, it should go for a default value. That's why blank has been defined over here. End case, end the module. So this is a way of writing the Verilog program for 7-segment decoder. Okay, students, how do we represent the memories in Verilog? So we are doing digital system design using Verilog, so it is very important for us to understand how do we represent the memories in Verilog. So have a look at this. Data RAM is a variable. It is 15 down to 0, that is 16 bit, and total memory locations are the size of the array is 0 to 4095. So this is 4K by 15 bit memory. So 4K locations are available, and each and every location is of 15 bit size. That's how we have defined the memory. So always at positive edge of the clock signal, if enable is high and if write is enabled, that means if WR is equal to I, which is nothing but write operation. If WR is equal to 0 means read operation. Enable is also high. What is that we have to do is data RAM of A, that means one of the memory location that is being taken from here. So from data, one of the memory location, for example 0 or 1 or something like that, put the data into that location. So D out is same as that of DN. So end the loop and end the behavioral block. Otherwise data output is equal to data RAM of A, whatever the stored memory that is available, stored data in the memory available, that will be taken as output over here. Okay, so this is where we have defined the memory. The first line says how do we define the memory. Size is 16, number of locations is 4K, enable is 1, write is also equal to 1. We are sending the data D in into the memory location. If write is equal to 0, that is read operation, that comes under else condition. D out is made equal to the stored data RAM of A means stored data from the RAM will be taken out and it is given as D out. So write and read, else is nothing but read operation. Here it is write operation. Okay, so this is how we represent the memories in Verilog. So these syntax are very much useful for you to write the Verilog program in the design of memories. In the next class we will be looking at different types of ROM. Just I am giving you the brief introduction of the memories available